So to find the value of P for equilibrium. And we also want to find the reactions at the bearing A and the bearing B. And information we're given, really everything is going to be reflected in the diagram and then in our free body diagram. They do give us information about the two bearings, and that will be reflected in our free body diagram. We'll start then, or we'll move on to the free body diagram. What is the object that we want to isolate from all of its supports and all of its connections in this picture? Right, so this yellow shaft that's going between the bearings. So the rod or the shaft is what we're going to be modeling. We're not including the bearing in our object at A or at B. So if we're not including the bearing itself, we have to include what those bearings do to the yellow shaft that we kept. And that also has these two applied loads acting on it as well. I'm going to keep the coordinate system that's given to us. So A is the origin in this case. Yep, you're right. Yep, points that way. So from here, the shaft comes down right in the negative y direction. It then goes down the negative z direction. And then continues in the negative y direction. And that's where we're going to be applying the force or holding this in equilibrium here. So there will be a force along that negative x direction with a value P that we're looking for. And this point does not have a name, but I will name this point D so that we can refer to it in our equations. On the other side, the shaft goes in the y direction, goes into the negative x direction, continues here, comes back onto the axis, and then goes through point B on the other side. And when it goes back, it has an 80-pound force being applied at a point I'm going to call C, since it's not labeled in that picture. In drawing my object, I've included those two applied forces, the 80 pounds and then the force from the hand at P. But I have that bearing at A and a bearing at B, and we need to include what those two supports that are not in this picture are doing to the yellow shaft that we did keep in the picture. We'll begin at looking at A. This is now, they're each a bearing, but we have to look at how it's given to us. A is a journal bearing, and B is a thrust bearing. So we now know which type of bearing A and B is, and they tell us that the two bearings are properly aligned. We need all of that information to know how do we model what's happening at A and what's happening at B. Starting at A, the journal bearing, what was the difference between the journal bearing and the thrust bearing? In a journal bearing, the shaft can move freely through the bearing itself along its longitudinal axis. In a thrust bearing, it prevents that motion. It can't move in or out of the bearing in a thrust bearing. A is the journal bearing, in which case, because it's a journal bearing, that means that the shaft can move freely through the bearing along its longitudinal axis, which in this case is aligned with the y direction. The journal bearing at A then does not prevent motion of the shaft in the y direction. Therefore, we're not going to put a force along the y-axis. However, what motion does that bearing prevent from happening at point A? Right, the shaft can't move along the z-axis and it can't move along the x-axis. Those two axes, really that whole xz plane is prevented. So we model that as a component of a force in the x direction and a component in the z direction. one direction is allowed, this XZ plane is prevented, so I model that as the X and the Z. And then we have to think about rotations. This is a round shaft and a round bearing, so the point of it is that it can freely rotate around the y-axis. And then the information about proper alignment comes in of do we include moments around the z-axis or around the x-axis. In this case, they tell us that it's properly aligned or that the two bearings are properly aligned, so the bearing does not exert any couples onto the shaft. So for the journal bearing that is properly aligned, or if it were self-aligned, we just have a force component in the x and a force component in the z, the two orthogonal directions to the longitudinal axis of the shaft. So for point A, those are the only two reactions that are going to be acting at point A. Right, moving on to B, our other bearing, which is, no, it's over here. B is a thrust bearing. We just discussed the difference between the two. The thrust bearing prevents motion along the longitude of the shaft. So in this case, there will be a BY. And just like the journal bearing, it also prevents motion normal to the direction of the shaft. So we'll have a BZ and a BX. Because the two are properly aligned, there was no moment at A, there's also no couples at B. Counting up our unknowns in this one, BX, BY, BZ, AX, AZ, and P, there's a total of 6 unknowns, and we know that we can get 6 equations out of a 3D free body diagram. But again, we want to check that. Just because we have fewer than 6 or more than 6 does not mean we're necessarily wrong. Some in the equations they'll be reflected, but if we have not 6, we probably want to just take a second look to make sure we modeled it correctly. Right, before we get to the equation step, I need the dimensions still for this. I'm just going to use coordinates to reflect that. So I want to put the coordinates of A, B, C, and D. Well, A is the origin, so it's already done. I'm using A as my origin. So D is located at 0, -10, -8. And we're in inches here. B is located at 0, 28, 0. And C is located at -10, 14, 0. Really the other geometry, because we're not considering the weight of the shaft in this, just that applied weight, the other dimensions of where it curls around really don't matter for this. All we care about is the places that couples and moments are going to be applied on our object. Now we have everything we need to start our equations. I'll start with forces in the x direction. From my free body diagram, I see that I have the applied force P in the negative x direction. I have AX in the positive, or I'm assuming it's in the positive, and BX in the positive. I have one equation but 3 unknowns, so I'll put it aside for right now. In the y direction, there's no AY. There is a BY, I'm assuming is positive. And that's the only force that's acting in the y direction. In this case then, from equation number 2, that means that BY is 0. It's a thrust bearing. It can prevent motion in the y direction. In this case, though, it doesn't have to. The free body diagram doesn't have to know that. We're just modeling what motions are restricted. The equation step will tell us, does it actually have to exert a force or exert a couple? If this problem were just a little bit different, if I were applying a force that did have a y component, say this way, then BY would be non-zero because I am trying to push the shaft along the y direction, and that thrust bearing would be preventing it. In this setup, though, BY is going to be 0. Finally, the z direction. I have AZ. I have BZ. and my applied 80-pound force along the negative z direction. I've used my equation 2. Between my two remaining equations, I have 5 unknowns for those 2 equations. So again, I'll just put them aside for right now and wait to have more equations before trying to do any of the algebra, because if I start to find numbers for these, it's going to be easier to solve equations 1 and 3 for my unknowns. I've used my 3 forces. Now I can take the moment around a point as a vector. Looking at the free body diagram, what point does it look like would be the most efficient to take the moment about? Right, B, I would say, because it has a bx, a by, a bz, so all 3 of those would be eliminated. In my notes, though, I actually did not do it around B. Based on equation 2, I already know that by is 0. So with that in mind, I would say A or B are equally good, knowing that by is 0. And actually, by goes through A anyway. So in my notes, I chose A. Probably more generally, B would be better if we did not know that by were 0. So just to follow my notes, I'll do it around A. By choosing A, AX and AZ do not appear in my equation, but I will have moment contributions from the 80-pound force, the stuff happening at B, and the applied force at point D. There are no couples in this, so I don't have like an MXI term or an MZK term, but I do have to have the R cross F terms from all the forces that are not acting through A. In this case, I'll have R, I'll call it RAD. This will be for the moment contribution of this force P. That'll be crossed with the magnitude P acting, or negative P I hat. I'll have a moment contribution from the 80-pound force. That will be RAC crossed with negative 80Z, or negative 80K. Again, just to reiterate, we're taking the moments about point. All of these position vectors will start at A, and they will all end where that particular force is being applied. The last one, RAB. Because BX, BY, BZ are all acting at point B, I actually will just do a single cross product here because I know what component has I, what has J, and what has Z. So I'll just say this is cross what I'm calling B, which is going to be the actual force at point B. So BXI plus BYJ plus BZK. I've accounted then for the 3 forces that are not at A, so I have to go and make these 3 cross products as my next step. RAD, fortunately, A is also a good choice because it's at the origin. I think that's actually why I did select it, which means that RAD is just a little bit quicker to find. So the points of D minus point at A, which is at the origin, I'll get 0, negative 10, negative 8. P is in the negative I direction only. And the position vector is being measured in inches. And the force, well, I know my applied force is in pounds, so everything here will be in pounds. The first cross product then is taken care of, RAC. Coordinates of C up top are negative 10, 14, and 0 inches. And that applied force is in the negative K direction, 80 pounds in that direction. And finally, at point B, I use RAB will be 0.280. And here, I want to put now the components, the correct components in the I, the J, the K of what I'm calling B hat here. BX will be in the I direction. BY is in the J direction, but I actually already know it's 0. So I'm just going to simplify it and put 0 there. But it would in general be by if we did not know it was 0. So I shall put by, but right away it's 0. And then bz will be in the k direction. Three cross products. I have 3 determinants. I have to expand out my determinants. A lot of things will cancel out because I have a lot of zeros in a row. I guess this is the one exception. So some of the I, the j, the k terms will cancel out. If I expand them all out and I group all my like terms, if I group all the I terms together, I get negative 1120 from the second cross product plus 28bz as my I coefficient. Grouping my j terms together, I have negative 800 plus 8 times p. And my k coefficients, I get a negative 10 times p minus 28 times bx. This one vector equation I split out, so my equation 4, I individually set my coefficients equal to 0. So for equation 4, negative 1120 plus 28bz is equal to 0. In my equation 4, my only unknown then is bz. bz then is positive 40 pounds. So at least my assumption of direction was correct here. Taking the coefficient in front of j and equating it to 0, negative 800 plus 8 times p. And also notice here, this has i's, j's, and k's. These 4, when I break it down, there's no i's or j's here because I'm only looking at the coefficients in equaling 0. I'm dropping out the i's, j's, k's parts from this. From equation 5, the only unknown I have is P, the applied force from the hand. P must be 100 pounds for equilibrium. And equation 6, looking at the K coefficient, negative 10 times P minus 28 bx. At this point, I know the value of P is 100. So in equation 6, the only thing by now I don't know is bx. I get negative 35.7 pounds for bx. I have 1, 2, 3, 4 of my unknowns solved for. Each of 4, 5, and 6, right away I got one of my unknowns. So all I have left is I haven't used my equation 1 or my equation 3. But now, from equation 1, I know the value of P is 100. I know the value of Bx is negative 35.7. At this point, the only thing left in equation 1 that I don't know is Ax, and that's 136 pounds. And finally, in equation 3, I know Bz now. So from equation 3, the only thing left I don't know is Az. So solving equation 3 for Az, I get 40 pounds.